Professor Belfrost's science class is back.
Hi, welcome back to this channel. And today we'll again discuss another concepts related to science. So here's the science tutorial for you today. Are you ready? Let's continue playing this video. Good. So this is our sixth lesson on the same chapter. We're still on the function chapter. I hope you still follow me so far. And today I will discuss about determining even and odd function. Actually, I have discussed a little about this. I mean, yeah, I've touched a little about this on our previous lessons, right? Okay. So some function exhibit symmetry, so their reflections result in the original graph. Yeah, for example, horizontally reflecting the toolkit function fx equals x squared or fx equals absolute x will result in the original graph. And we say that these types of graph are symmetric about y-axis and it is called even function. Okay, so y-axis is symmetric. Okay, so this is even function. But for example, we have x equals x cubed and the reciprocal x. They are reflected over both axes. For example, like this and this. See? So it's shown in figure 17. Figure 17. We say that these graphs are symmetric about the origins, and the one that is like this is called odd function. Okay, and a function can be neither even nor odd if it doesn't exhibit either symmetry. Okay, so an even function is when fx equals f minus x, and an odd function if fx equals minus f minus x. And this is the three rules that we have summarized. Okay, so example, is the function fx equals x cubed plus 2x even, odd, or neither? So without looking at the graph, actually you can determine whether the function is even or odd by finding formulas for reflection. Okay, so x cubed, it is, yeah, odd, and for 2x, it is odd too, right? So it is an odd function. Okay, and you can also solve it like this. So you try with the rule of even function first. Is it the same thing if we substitute minus x into the equation? And you find out that, yeah, this is a return to the original function, so this is not even. But when you test with the rule of the odd function, yeah, minus f minus x equals fx, so this isn't in this is indeed an odd function. And this is the graph for the last figure, last example. Now graphing function using stretches and compressions. Okay, so practical stretches and compressions is the first one. So when we multiply a function by a positive constant, that we get a function whose graph is stretched or compressed vertically and a ratio to the graph of the original function. If the constant is greater than 1, then we get a vertical stretch. And if the constant is between 0 and 1, then we get a vertical compression. For example, like this. You can see it, right? Okay, so this is the original one, the black one, fx. And if we stretch it, it means that we multiply with the constant greater than 1, it will be stretched. And if we multiply with a constant that is less than 1, it will be compressed. And this is the summary. Okay, so let's dive into the example. For example, we have this one graph that shows the function pt that models the population of fruit flies. And the scientist is comparing this population to another population Q whose growth follows the same pattern but it's twice as large. So it means it's stretching. So sketch a graph of this population. Actually, it's easy, right? You just need to stretch it. Okay, 1 to become 2, and you can just take the one that is whole number. It's easier. 3 to become 6, and yeah, you just stretch it basically like this. And symbolically, I mean that the relationship is written as qt. For example, you take qt as the transform function equals to pt. So it means that the value of function q is twice the value of function p. And given the tabular function, assuming that the transformation is vertical stress or compression, that create a table for vertical compression by determine the value of a and multiply all of the output values by a. Now let's see the compression. For example, in this case, we multiply with the halves. With a half, then we see it's just half. This is just 3 half. This is 3 halves. This is 11 halves, like this. I want you to solve this for your assignment. Next, we have graph in figure 22, which is x cubed, and relate this function gx to fx, and then find a formula for gx. So if you see, x cubed should be 1, right? But here you only see this is about a quarter. Maybe you are still not sure, but let's see when we make a 2 cube. 2 cube should be 8, but this is only 4, right? How about uh yeah, the same one is here, minus 2 cube. It should be minus 8, but here you only have minus 2. It means all is 1 quarter from the original value. So this is 1 quarter of x cube. It's easy. Okay, it's quite simple, I mean. Okay, now let's discuss about horizontal stresses and compressions. So this is when we consider changes to the inside of a function. So if the constant is between 0 and 1, then we get a horizontal stretch, and if the constant is greater than 1, then we get a horizontal compression of the function. Okay. So this is the one that's shown. Okay. For example, x squared is the original one, which is the blue line. Then 2x squared, the one with a greater constant, it means that we compress it horizontally. Okay, it's just, what is this, Tosca maybe, I don't know. And if we multiply with half, it make it wider, so horizontal stretch. Yeah, this is the rule. Now, graphing horizontal compression. Suppose a scientist is comparing a population of fruit flies to a population that progresses through its lifespan twice as fast as the original populations. In other words, that this new population R will progress in 1 hour the same amount as the original population does in 2 hours, and in 2 hours it will progress as the original population does in 4 hours. Sketch a graph of this population. So symbolically, we can write like this. Okay, R1 equals P2, R2 equals P4, RT equals P2T. Okay, and here's how the transform population. You see, because we always have the constant is larger than 1, greater than 1. This is compressed. This is the effect. Now finding a horizontal stretch from a tabular function. So J equals f of half x. So yeah, actually this is a stretching, right? So yeah, if you want to create a table, it's easy. It means this is 4, this is 8, this is for 12 now, this is for 16 now. The gx is the same. Now recognizing a horizontal compression on a graph. So relate the function gx to fx in figure 26. If you see this is a compression, right? We have 2 here, we have 6 here, so it is compressed by 3. It means that the constant is 3. Okay, so gx equals f 3x, and this is a horizontal compression by 1/3. So when combining transformation, that is very crucial to consider the order of the transformations. For example, vertically shifting by 3 and then vertically stretching by 2 doesn't create the same graph as vertically stretching by 2 first and then vertically shifting by 3, because when we shift first, both the original function and the shift get stretched, while only the original function gets stretched when we stretch first, okay? And when we see an expression such as 2f(x plus 3, which transformation should we start with? The answer here is the one that we do as the order of operations. That given the output value of fx, that we first multiply it with the constant 2 that cause the vertical stretch, and then we add 3 to cause the vertical shift. So multiplication will always go before addition. Okay, how about horizontal transformation? It's a little trickier. For example, we write gx equals f of 2x plus 3. So it means that we have to think about how the input of the function g relates to the input of the function of f. That's supposed to have f7. Okay, it means x equals 2, right? So it's different. It's different way. So for example, we have like this. We can factor it like this. Okay, so you observe a horizontal shift to the left 2 units. This is the inner part. And then we have a horizontal compression because we have factor constant. And then factoring this way allows us to horizontal stretch first and then shift horizontally. So this is the rule that you need to pay attention to. So given table 15 here, the below part, for the function fx, the create table of values for the function gx equals to f3 to f of 3x plus 1. So you see you have 6, 12, 18, 34. It means you have 3x here. It means that it's compressed 3 times. So it is 2, 4, 6, 8 now for the f3x. And then you multiply 2 times, so a larger 2 times the row below. And then you add 1 to the output. Easy, right? And then use the graph of x in figure 37 to sketch a graph of kx equals f half x plus 1 minus 3. With this, how you solve it? Actually, it's simple. First, you stretch it horizontally with factor 2, right? You stretch it with like this. And then plus 1. It means shift left 1 unit, like this. Okay, and then you shift again 3 units. You shift down, I mean 3 units. Oh, I'm sorry. Actually, it works like this. Half x plus 2, okay? So it means that you need to first stretch by 2, then you shift 2 position to the left, okay? Horizontally. Now absolute value functions. Okay, so yeah, recall that absolute value function can be defined as a piecewise function that x if the fx equals x if x greater than equals 0, and fx equals minus x if x less than 0. So let's see. Yeah, plus minus, it is a tolerance range, okay? So yeah, actually it's self-explanatory, okay? 5% of 680, it is 34, right? So the absolute value of r minus 680 is less than or equals 34. And then you can see, okay, So graphing an absolute value function. Let's see. Okay, so writing an equation for an absolute value function given a graph. Oh, I skipped this. I'm sorry. For example, we have y equals absolute x figure like this. So if we are to graph this function, it means that first we right shift it with 3 units like this. Then we stretch it 2 times, and then we uplifting it 4 units, right? Yeah, that's easy. And by seeing this, what do you think it is? It has been moved 3 position to right. It has been shifted. Then it has been stretched again, right? It should be on the original position. Uh, this has been compressed 2 times, right? So it should be this one, right? And as we also uh, downlift 2 units. So this is the functions that describe. Now solving an absolute value equation. Actually, this has already been discussed on the previous lesson. But let's see if there is something that we haven't discussed. Find the values of x such that f(x) equals 0. Yeah, you just substitute it. 0 equals absolute f 4x plus 1 minus 7. And we move the constant to the other side. And yeah, as you have known, this must be minus 7 and also 7 like this. And then we can plot it. So x equals 3 halves and x equals minus 2. The last topic, I think, is inverse functions. So a reversible head point is implemented. Okay, you see. So we first learned how to verify that two functions are inverse functions. Okay, so inverse function is a function for which the input of the original function becomes the output of the inverse function. The output of the original function becomes the input of inverse function. So it's written like this. So if we have a function fx that we represent its inverse, I mean the inverse of the function fx as f raised to the power of minus 1x, okay, or this is read as f inverse of x, okay. So yeah, the raised minus 1 is a part of the notation, and this is not exponent, okay. So this is not a power of minus 1. I always say minus 1. Well, so this is not mean 1 over fx, because 1 over fx is just the reciprocal of f and not the inverse. So what it means is that when f inverse dot fx, it equals to x itself, okay. So for example, for x and quarter x, they are both inverse function to each other, because when we insert it, it will result in x, okay. And or there is no matter which one comes first and which one comes last, okay. So if for a particular one-to-one function f2 equals 1, f5 equals 12, there were the corresponding input and output values for the inverse function. It means that f4 equals 2, I mean f inverse 4 equals 2, and f inverse 12 equals 5. So g4 equals to, for takes for example the inverse function f minus 1, okay, is g, so g4 equals 2 and g12 equals 5. Okay, so this is another example. If fx equals 1 over x plus 2 and gx equals 1 over x minus 2, so is g equals f inverse? So you just need to make the composite function. So for example, you take fx as the candidate. So 1 over x plus 2, it means x plus 2 minus 2 is x. Okay, and actually this is already enough to say that this is yes, but you can also verify it the the other ways. For example, you take this as the um, base. Okay, so 1 over x plus 2, and insert this. So this is 1 over x minus 2. So is 1 by 1 over x. So this is x2. So these both are inverse function to each other. I will need to try to solve this. Now, if fx equals x cubed and gx equals third x, so if is g equals f inverse, yeah, and this book has shown us that these are not inverse. Now, finding domain and range of inverse functions. So the opposite function f are the inputs of the f inverse, so the result of f is also the domain of f inverse. And likewise, because the input to f are the outputs of f inverse, that the domain of f is the range of f inverse, and we can visualize the situation as shown in the figure 3. Okay, so it's just straight side, okay, domain, range. When a function has no inverse function, it is possible to create a new function where that new function on a limited domain does have an inverse function. For example, the inverse of fx equals a square root of x is that f inverse x is x squared, because a square undoes a square root, but the square is only the inverse when it comes to the domain of from 0 to infinity, because you cannot square minus number, right? You cannot square negative number. Okay, so given a function, if you need to find the domain and range of its inverse, you need to follow these two steps. Let's dive directly to the example, finding the inverse of toolkit functions. Yeah, so if we see, if this is x, this is x squared. Yeah, first we have we did, okay, you can see this. Okay, next, finding and evaluating inverse function. First, inverting tabular functions. Okay, so this is very easy. We only need to interchange the domain and range. That each row or column of input becomes a row or column of outputs for the inverse function. Okay, so a function ft in table 3 showing distance in miles a car has traveled in t minutes, and find and interpret f inverse 70. F inverse 70 means it is 9, 19. Easy, right? This is your assignment. Evaluating the inverse of a function, give a graph of the original function. Okay, this is again not very difficult. You just need to follow this step. Okay, so G3, it is 1, but G inverse 3, it is 5. Okay. Now finding inverse of function represented by formulas, you just need to follow these 3 steps. Okay, you just need to rearrange the term as shown. Find the inverse of function fx equals to over x minus 3 plus 4. So first you rearrange it like this and create this. It means that now this is the f inverse function. And now you can create the table of the inverse function. Find the inverse. Again, this is easy. You just need to group it and change the arrangement. Y become x and x become a straight side. This is how you do this. Okay, by analyzing the graph, it is not difficult to. You just need to, yeah, create the projection by y equals x. Okay, you just create the reflection and yeah, actually that's all of this chapter we have done. Before I end this video, I want to share you a good quote from Aristotle. So the roots of education are bitter, but the fruit is sweet. And yeah, that's for our lesson in this chapter, and we will go to the review session on next video. Okay, that's the end of the video for today. Thanks for watching. Thanks for following so far. And here's what you need to do. Please subscribe, give a thumbs up, comment, and share this video to your friend. And also, don't forget to check our website at https://science with exploits.unaux.com, and I'll be back on every Tuesday, so keep watching and be thoughtful. Goodbye, see you on the next episode.